Welcome back, Algebra Express. We are in Rockswold 2.4. So this is more modeling with functions. So in this, we're going to talk more about functions, and more specifically, we're going to talk about linear functions. And so a large part of this is sort of a review of things that we've kind of already done. And then we're going to probably talk about like two things that are probably about new. Direct variation and piecewise functions. And so we're starting off here. So this should pretty much be a review. So we're doing slopes and intercepts. So we want to pick off the slope from this thing. We want to pick off the intercept. If we're looking here, our slope, our intercept is 0 to 15. We're looking at the y-intercept. If we're doing our slope, this is going down 15 for every 2 that it goes over. So our slope should look something like minus 15 halves. And so if we're going to put this together, instead of y equals mx plus b, we're doing a linear function now. It's f of x equals mx plus b. So we're doing just a linear equation with function notation is what we're doing now. And so now we're doing f of x equals, and I'm going to plug in m is minus 15 halves. So this is mx, and we want to do plus b, which is 15. Okay. So now we're finding a linear function. It says exactly the same thing I just said. Remember, a linear function is the same as a linear equation. We're just changing the y to an f of x, basically. So now instead of saying y, we're saying f of x. We're changing the notation just a little bit. So if we want to look at this thing, this is f of 2 equals minus 3, f of 4 equals 7. So this function notation is the new thing that you just learned. So relate it to the old thing you just learned, and instead of writing it like this, I would suggest writing it as an ordered pair. If we're looking at this thing as an ordered pair, we can look at this thing as being the point 2 is my x, and this is my y value. And if you write these as points, we're trying to find a linear function that goes through those points. And we know how to do that already. So we know how to find a function that goes through 2 points. Let's think about how to do that again. So you have 2 points. In order to find a linear function, you need to put it into either slope intercept or point slope. So we're going to go for point slope since we don't have an intercept. So we need to do point slope. And for point slope, we have a point, but we need a slope. So always, if you don't have a slope, that's almost always going to be the first thing that you find. If you're going to find a linear function, you need a slope. So we're going to go 7 minus and minus 3. We're going to go 4 minus 2. Giving me what? 10 over 2 is 5. Now, so I have my slope is 5. I have a point. I have 2 points to choose from. I'm going to go with the first point. So y minus a minus 3 is equal to 5, and then going to x minus 3. So this is y plus 3 equals, we're going to do some distribution here. Here's 5x minus 10. And now we're subtracting the 3 over y equals 5x. Subtract the 3 over, we're going to go minus 13. Okay. So they want us to find a linear function f. So there's one little thing I have to do here. This is y equals 5x minus 13. I have to convert this to function notations. Instead of y, I just write f of x equals 5x minus 13. Okay, so we have this function, and the last little question on this page, if I pull this down, it asks us what f of 5 is. So if I'm looking at my function, bring my function back up here. Part A says, and so how do we know what f of 5 is? So f of 5 is plugging in a 5 everywhere there's an x. For f of x, it's like 5x minus 13, so f of 5 is going to look like 5 times 5 minus 13. So if we do that, now we got some order of operation stuff. So 5 times 5 is 25 minus 13 is going to give me what? Total of 12. So f of 5 is going to be equal to 12. Okay. So the next page is pretty much a review as well. This is student activity. So this is about straight line depreciation. Suppose that a new computer is purchased for $1,800, and straight line depreciation is used to estimate its value over 4 years. That is, after 4 years, the computer will be worth nothing. Find a function that expresses the value v of x of the computer as a function of its age x. Okay. So there's two important sort of things I'm reading here that they're giving us. Suppose that a new computer is purchased. So we start out, it's cost $1,800. After 4 years, it is going to be worth $0. Okay, so the value, so there's a few ways I can think about this. The value at year 0 is 1,800. Is one way I can think. Or they're giving me the value at year 0, it is what, 1,800? And so my x is the year, my y or my v of x is the 1,800. That's the value of the computer. And the other thing, after 4 years, the computer is going to be worth $0. Okay, so they want us to calculate a function for this. So we have 2 points, and so this should be pretty similar to the thing that we have on the previous page. We have 2 points. We need to create a function between it. So I'm going to go and use like probably x and y notation and then convert it to my function notation at the end, like I did previously. I know how to do things with linear equations and things like that, and just throwing in the function notation, I think it's going to cloud things a little bit. And it's easier just to convert the variable at the end. So let's go about this. We have 2 points. If I have 2 points, the first thing I need to find is the slope. So I'm doing 0 minus 1,800 over 4 minus 0. I'm probably going to use a calculator for that, but it's not too bad. You can probably do it by hand. Minus 450 is what this thing is going to give me. This top is going to be negative. This bottom is going to be positive 4. So half a slope is a minus 450. I can actually go straight to my slope intercept form. So I want to go to slope intercept. I want to do minus 450 is my slope. That has an x attached to it. And I'm going plus my intercept up here is 1,800. Okay, so maybe I need to do like some converting to like function notations. Instead of y, I'm writing v of x and writing everything else down exactly the same. Okay, so what's the next thing I do is graph the linear function. Okay. So if I want to graph this thing, I know on my y-axis, I'm going from, well, let's start with the x. I'm going from 0 to 4 on my x-axis. So I think there's 10 tick marks. And so I think if I go every 2, that should take care of what, 8 tick marks, I believe. That's probably pretty sufficient. And in the y, I'm going from 1800 to 0. So I need to do 1800, and there's about 10 tick marks. So if I do 1800, I have to divide that by 10 tick marks. So that's giving me about 180. So I figure I don't want to count by 180s. I probably want to count by 200s just to be safe. And because it's easier, right? So do every 200, 200. Okay. So I know one of them is 0, 1800. I know the other one is 4, 0. And this is what's referred to as what, straight line depreciation? I think it's back to that. It starts off at a value of 1800. After 4 years, it's going to be worth nothing. So this is a reminder that when you draw something by hand or when you draw a graph, it is not the most accurate sort of representation. If we're asking for a number or something, we want you to solve it symbolically. Don't just like try to guesstimate a number off the graph. So what is the implied domain here? So if I'm looking at my graph, the domain is the x values. So if we're looking over here, I didn't label it. I didn't label a lot of things. And so I have a graph. If I'm presenting this graph, I really should label a lot of things that I didn't label. So on the bottom here, these things are my time. My x value is in years. So I should say something about this being years. I should say something about this being the money. And this whole thing is to represent a value of a what, computer. You put a title on the whole graph, and then you label your axes if you want to have a nice little presentable graph that makes everyone happy, right? And so I'm getting a little bit ahead of myself and not labeling things, but getting excited about math. What can I say? This is 1800, starts out at 1800, goes 4 years to nothing. So what is the implied domain? That is our x values. And so we're going from 0 to 4. So this and thing about the implied is like there's some like real world sort of restriction on this thing. And so one of them is that it has to be positive. So we start out at 0 years. It can be 0 or positive. So we start out at 0. It can't be negative, I guess, is a more proper thing to say, right? We can't have a negative number of years. We can go up to 4 years, but after 4 years, we don't really want to talk about something that's worth nothing. We don't want to talk about the value. It's kind of silly. So after 4 years, it's worth nothing. We don't need to talk about its value anymore, and we can't get nothing from it. What is the value of the computer after the first year? So again, we don't want to rely on our graph necessarily. But if we look after the first year, that is when our x value is 1. If we plug in 1 for our x value, we're doing 1800 minus one set of 450, basically. We're going to subtract 450 from it once. That's another way to think about it. If we subtract 450 from 1800, that is going to give me 1350. And so it should be 1350. Let's look at the graph and see if that is accurate. 1 year. It's... Whoa. No, let's look at the right line. Yeah, it's a little low. That's why you don't want to rely on your graph. When will the value of the computer be 450? So there is probably a really cheap way to think about this one, but I'm going to say it right after I try to solve for this. So if my equation looks like this, the equation up. There's my equation. And so what I want to do is I want to know when this thing will be a value of 450. And so they're giving us a two-variable equation. So the first thing was what will the value of the computer be when the year is after 1 year? And so that we plugged in 1 for the x. And so now they're asking what will the year be when the value is 450. So now we're plugging 450 into our other variable, our v of x, and solving for x. And so now we're solving this thing for x. We're looking at this thing. In order to get x, we have to subtract 1800 from both sides. So this is going to give me minus 1350 equals minus 450x. If I divide both sides by negative 450, I'm going to flip the axis here. So my x is on the left. So I'm getting 3. And let's go back and look at this sort of thing. So when will the value of the computer be 450 after? And let me write this thing right here, b of x, so we have anything to look at, minus 450x. What was that? Let's say 1800. That was the equation of this thing. And so if you think of when will the value of this thing be 450, there's kind of a cheap way to do it if you think about this. After 4 years, it's going to be worth $0, and it's going down by 450 each year. So it'll be 1 year before it's worth $0. Again, my line looks a little bit low. It looks like it's going through about 400 instead of maybe a little bit higher. It should be a little bit higher, around 450. Okay. All right, the next page is pretty much a review as well. We're looking at this thing, we're seeing how much it goes up by each year. If we look on the x-axis, we're going up by 2, we're going up by 1, we're going up by 1, we're going up by 2. And if we look here, it's going down by 1.2, it's going down by 0.6. It's going down by 0.6, and here it's going down by 1.2. So we want to know if this can be modeled exactly by linear functions, what this thing asks. So find the function. So if we're looking here, what we're checking to see is if the slope is the same. So we've done it before. Two, the same thing. All of these things are the same. There's basically two numbers we gotta check because it repeats, right? But those are all the same thing. They're all minus 0.6. Reminder, our slope is the y over the x. Sometimes people will flip that. So I know that the table is kind of flipped from the way that we find the slope. Okay, so we have our slope, and we want an equation. Function. I guess we'll just f of x. So f of x equals mx plus b is what I'm doing. So I want to do mx plus b, so I'm going minus 1.6x. I want to do plus b, which is 4.8. Now we're looking at this thing. This thing goes up 1. This thing goes up 1. It's going up 1 each time in the x. Here it's going up 1.8. Here it's going up 2.6. I don't really have to continue, but it doesn't even stay the same each time, I believe, right? It goes up like 2.4 and then 2 when it's crazy. So if it does that, we've already talked about this. This is not linear. Why is it not linear? Because there's no slope, right? Because the thing about slope is the slope has to be constant. This is not a constant rate of change. This is jumping all around that place. So we're going on to something a little bit new. So this is a little bit new, but it's only new in the way that we're using our vocabulary, I think. So if we see something that looks like y varies directly as x, the first thing I want you to think that pops in your mind is that y equals kx. And I say this isn't really totally new because if we just look over here, if we do something like plus 0, you might notice this is just a linear equation that goes to the intercept, right? So we kind of know what this thing looks like already. It's going to be some sort of linear equation. There's just some kind of constant that we're multiplying by x. If we think about it, y varies directly as x. So what that really kind of means is that if x goes up, y is also going up. And if x goes down, y is also going down. And so we will talk about varies directly. We'll talk later about something called varies inversely. So this is what varies directly looks like. So the first thing I want you to think, erase this from your mind, y equals kx. If you see the words varies directly, y equals kx. There's some kind of constant or coefficient I need to find. K is called the constant of proportionality or the variation constant. So we have an example here, the UT tower. The table represents the distance you are from the UT tower as a function of the time it takes the sound from the tower to reach you. So what is the value of K? This is like my X. This is like my Y. And I know it varies directly. Say that directly in this problem. So don't say that in this problem. So I think they're just wanting you to sort of imply what you know probably about the thing. The further away it is, it's going to be directly proportional from the intensity of the sound. And so the further away you get, the longer it's going to take, right? So y equals kx is the formula that we want to use. This thing varies directly. So here they're giving us 2 points. We could plug in 0 and 0. But you might notice that doesn't help you solve for k for very much. It just gives you something like 0 equals 0. So that point's not going to help you a whole lot. So we want to look at this point. So when my y is 680, my x is the value of 2. So when my y is 680, my x is the value of 2. So almost always when we give you a sort of like things are directly proportional problem, almost always the first thing you're going to do is solve for that constant of proportionality. So if we're looking at this, my k value is 680 divided by 2. So my k value should be 340. So what is the value of k? The value of k is 340. What is the meaning of k? Thinking about this thing. Or so, this is the general formula. This is the specific formula to talk about this sound from the UT tower. So now we've found an equation to talk about the sound from the UT tower and how far you are from it versus how long it's going to take for the sound to travel to you, right? And so we're thinking about this. This is like our slope here. And so we're going to interpret this thing, our constant or our coefficient, what do they call it? The constant of proportionality. We're going to interpret this thing like a slope. So it's like 340. And it's the change in y per the change in x. So what this is saying is that every 340 meters, for every 1 second, the sound's going to travel. What did I say in limits? The sound travels 340 meters per second. Okay, and the last thing they ask us to do is to fill in the equation. So if x is 1, we're going to do 340 times 1. Should give me 340. If x is 3, we're going to do 340 times 3. Should give me 1020. Okay. So I want to do something a little bit different. I want to go to the last page first. So that problem on the 4th page is a bit like cumbersome. I don't think it's the best example to introduce piecewise functions with. So I think this might be a little bit better. Okay, where to go with my pencil? So what is happening here? So I actually have several lines here is what is happening. I have one that looks like y equals 2. I have one that looks like y equals 2.69. So I know this says f of x, but if we think about these things, the y equals 2 line is this line happening right here. If I draw a y equals 2 line, if I draw a y equals 2.69 line, it's going to look like this. And so we have a bunch of lines, and you might notice they are all constant functions. So we have 4 lines here. So we have 4 different equations, but we don't want the entire equation. So for y equals 2, I only want from 0 to 1 on the x. So if I look from 0 to 1 on the x, and I erase all this other line, and I erase all the other part of the line that's not from 0 to 1, I get what's remaining here, what's drawn here on the paper. Same thing with this. I'm only from 1 to 2, so I go from 1 to 2 in the x. And I'm chopping it off. I'm chopping it off everywhere that's not 1 and 2 in the x. And I'm chopping them off, and I'm chopping each line, right? I'm chopping each line into a specific domain. And so we're piecing these lines, these segments of these lines together to form these things called piecewise functions. And so this is representing, what do they say, a cost of a call when roaming overseas. So it costs $2 to place the call. It costs 69 cents per minute after the first minute. So this is also what they call a sort of stair-step function. It looks like a set of stairs. And then maybe another thing to notice is we have these endpoints here. So it does not include the 0. It does include the 1, so it's a solid dot. This one does not include the 1, but it does include the 2. So it goes from solid to open to solid, open to solid, open to solid. If you look here, it goes from not including to including, or open to solid, open to solid, open to solid, open to solid. So hopefully we can notice some similar sort of patterns happening there between the graph and this domain restriction happening over here. So we go f of 2.1. If we think about this, this is like an f of x. So this is telling me my x is 2.1. So when my x is equal to 2.1, which one of these am I going to use? So I'm only going to use the one where my x falls in. So 2.1 falls between 2 and 3. So I'm only going to use this one. So a lot of times, I don't know, I'm not sure why students do this, but they will see it and they will give me like every single number here and they will put it down here, or they will try to add these numbers or something. We have a restriction on the domain is what this piecewise thing means. We're like deleting parts of this domain. We're restricting it. So we have to look where it falls in the domain. So whatever x value they're giving me, I have to see where this x value is going to fall over in here, right? I have to look over in here in these intervals, and I have to see where this thing's going to fall. And so this thing falls between 2 and 3. So I'm using this line right here where it says 3.38. And if we look at 2.1, like I said, it's between 2 and 3. It's like right in here. That's going to be the 3.38 line over in there. So maybe if you think about the graph being pieced, we don't want all those numbers. We only want the one that matches it, right? So you got to be really careful about that. So is the function continuous on its domain? So I know I skipped over that in the previous page. So there's 2 ways. How are they defined? Grab it here. They define continuous as no breaks, is what they say. There's no breaks in the graph. It is continuous if you do not have to pick up your pencil. So if you can draw this thing without picking up your pencil, then it is continuous. And so if you can draw this thing without picking up your pencil, I'll give you some money. I don't think you're going to be able to do it. You have to come here. You have to pick up your pencil here to get to this next line. You have to pick up your pencil here to get to this next line. So we'll probably see something on the next page or this page that is continuous. This thing is definitely not continuous. Okay. So this thing we want to graph. So we want to graph a piecewise function. So remember, there's three things here I want to graph then. So one looks like y equals minus 3. There's another one that looks like y equals x minus 2. And there's another guy that looks like 0.5x. Ooh, y equals 0.5x. Let me repeat that. And so there are two sort of ways that you can graph this. I'm going to graph it two sort of ways. I'm going to go about it this way. The first way, I believe, will like get behind the more of the mechanics of the piecewise and why it's called piecewise. And the second way is probably going to be the way that I'm going to graph things. So if you want to look at both ways before you decide how you do things, I won't blame you there. So y equals a minus 3. So let's graph that thing 1, 2, 3. Minus 3 is down here. It looks something like this line. This is my y equals minus 3. The next thing is y equals x minus 2. I'm going through the minus 2. I'm going up 1 over 1, up 1 over 1. Up 1 over 1 graph. I can graph that thing. And the last one, y equals 0.5x. So this I'm going to write as 1 over 2 or a half x. So I'm going up 1 over 2. I'm going through the origin. I'm going up 1 over 2. I'm going up 1. I'm going over 2. Down 1, up 2, down 1, left 2. Okay. Now I want to look at these domain restrictions. And so I'm looking at this first one. I'm going from minus 4 to minus 1. 1, 2, 3, 4. I'm going to draw it with some pen maybe. Minus 4 is right. And the next one is a minus 1 to 2, so 2 is right here. And the next one is from 2 to 4. So the next one I want to go is 4 is right here. So I'm dividing my domain up by these values. This is the minus 4. This is like the minus 1 that is up here. This is the 2 and the 4. Coming from these domain restrictions. So I look at my y equals minus 3. I only want this thing from minus 4 to minus 1. So I only want this thing that part of it. Now I look at my x minus 2. I want that from minus 1 to 2. This one is my x minus 2 graph. So I want this thing, but I only want this thing from here to here. Parts I wanted. And the last part is the 0.5x graph, but I only want the 0.5x graph from 2 to 4. So I'm erasing it. So I have my segments that I need. I need this segment, I need this segment, and I need this segment. Okay, so now we're looking at this thing. Now I need to determine my endpoints. So it should be solid and solid on the minus 3. So this is a solid endpoint. Ooh, this is a solid endpoint. And I'm getting that from the inequality is inclusive. So I include my endpoints. This one is not inclusive. So this endpoint should be open. But we have an open endpoint over a closed endpoint. It becomes closed. We include the point. So it's still there. This one should be solid because this thing up here is inclusive. This one should be empty, and this one should be solid. So that is a lot of work to get that graph. That is not how I would go about doing that thing. I would do it a little bit quicker. Okay, so if you look back at this graph, I drew this whole thing, but really what I was only interested in was this little part. So if I look at how this thing is kind of defined, I can kind of define this segment by its endpoints. I'm really only interested in these endpoints. I know these are all linear functions or constant functions, which are also linear, right? With the slope of 0. So they're all linear functions. They're all going straight from one point to another. And so if I graph the endpoints, I should be able to graph this thing. And then I didn't answer it, but is this thing continuous? Can you graph this? We can graph it from here to here. And we saw how like that open endpoint and the solid endpoint and the empty endpoint become a solid endpoint, right? So there's no skip over here. This is a continuous portion, but when we get to here, we have to pick up our pencil to draw this thing, right? And since we pick up our pencil from the 0 to the 1 here, this is not continuous. This is definitely not continuous. So we know what this looks like, and I kind of told you how I'm going to go about it. So we want to do things from the endpoints. So this is kind of how I think I structure it. Y equals a minus. Y equals minus 2. Y equals 4. Okay, so I'm looking here. I want to graph my y equals 3, and I want to graph it. It's going to be a solid at x equals 4. And it's going to be a solid at x equals a minus 1. And so if I'm looking here, if I'm looking at these points, minus 0.4. Let's go ahead. Let's graph this right quick. Ooh, 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 ooh. I like completely draw my negative sign. So x is a minus 4. Ooh. Ooh, so let's rewind just a little bit. This is a constant y equals x minus 3. So I want to do a solid x minus 4 minus 3. And I want to do a solid at x equals a minus 1, which is the other bound here. And that's going to give me a minus 1 minus 3. So let's get our x and y's correct, and it will help a little bit with graphing, probably a lot bit with graphing. So let's do this. So minus 4 minus 3 is the first point I want to graph. So minus 1, 2, 3, 4, minus 1, 2, 3 is the first point I want to graph. The next thing is minus 1, 2, 3. Ooh, let's get this up here. And so those are the 2 points I want to graph. They're both solid. And so I'm graphing from this point to this point. And hopefully this makes sense. This is a constant function. It should be flat. Let's not go by that point at all. The next thing is x minus 2. So I want to graph y equals x minus 2. The first thing is a column. X equals minus 1. A solid point at x is equal. But what I'm doing is I'm plugging in this x to this function to find my y. So if my x is a -1, -1 -2, give me a -3. So that's the point I want to graph. The other thing is the x value of 2. So when x is 2, I'm doing 2 minus 2, which is giving me the point 0. So I'm doing -1 -3. I already have that one graphed. So I'm doing an empty circle here, but it's already a solid circle, so it just stays there. I'm starting here, and I'm going to 2, 0. 1, 2, 0, and I'm doing a solid dot here at 2, 0. I'm drawing my line in between. And now the last part, the third part. So I'm doing a open circle at x equals. Circle at x equals. So if x is 2 and we're going to have 2, that's going to give me 1. If x is 4 and we have 4, that's going to give me 2. So we're plugging x into this equation. We're using this equation now for this portion of our domain. So basically what we're doing is we're piecing this thing, and we're using a different function for each piece of the domain, right? We're using a constant function, we're using a linear function, we're using a different linear function. So we're doing 2, 1, 1, 2, and we have to do 1. So we're going 1 up, and this is the open circle. So that was the gap in our graph that we saw previously. So we're going from 2, 1 to 4, 2, 1, 2, 3, 4, and we're going up 1, 2, right here, and we're drawing a line in between them. And so obviously it is still not continuous. Nope. But we have our graph drawn. It's a little bit cleaner than the previous page. A little bit prettier. And I think this is probably the way I'm going to go about things for the most part. If you have to piece your domain or write some, draw some lines up and down, that's fine. Whatever helps you to see it. As long as you can interpret it. And I can interpret it somewhat. Okay, so the last page. This is how they try to start you out with piecewise functions, which I'm not really sure why. This thing looks way more complicated than the previous page. So we have a progressive tax system that taxes you based on your income brackets. And so on the first $6,000, you're going to get taxed 10%. And so if you get taxed 10% on $6,000, you might notice that's a total of $600 that you would get taxed on that. So on the next $6,000 to $26,250 that you make, you're going to get taxed 15%. But they're not going to re-tax that first $6,000 at 15%. They're only going to tax that at 10%. So we're starting out with $600 tax from the first $6,000 that you make. And then you're going to make 15% on anything that is over $6,000. So if we combine that, we know 15% of, now they're doing the same sort of thing, same sort of pattern with the next step. We can go 63,000, more am I at? If you make anything over 26,250, that first 6,000 to 26,250 is getting taxed at 15%. It's not getting taxed at 27%. So we can calculate 10% of 6,000. We can calculate 15% of what? 26,250 minus 6,000. Yeesh. We can add those two things together, and we're going to get this number. So we can keep stepping this thing up based on how much you're making and tax you more on the larger amount that you make. So the next thing, where are we at? They want us to find, they give you this sort of thing. And so this is an example of a continuous graph. So if we look, it starts here and ends here, starts here, ends here, starts here, ends here. Okay, so now we want to crunch this f of 68,000. So if you're making 68,000, this is like my x value. So this is sort of like those brackets like we were seeing earlier. We're looking at these ranges in our domain, these values that the domain goes from. So 68,000, I believe, is going to put us right into this thing. It's going to be between 63 and 132, right? Okay. So this is the line that each we want to look at. We're doing this with a linear function. This is a cumbersome example. So we're going to get taxed. We're going to get a base rate of 13,708.50. So this is a linear function. These are all lines. It is a linear function. So this is a base rate. So this is sort of like my B, my Y, right? We're going to start out at that rate. For y-intercept, I need a slope and an x value. So my slope here is kind of like my rate. So my rate here is going to be 30%. And this is where things maybe get a little complicated. We want to do 30%, but we want to do of the amount over 63,550. So maybe do a little bit of math. I guess I can do it beforehand. I threw it all in one equation, but we want to do 68,000 is the number we want. We want to know how much larger that is than 63,550. Let me write the right numbers down. So we want to know how much larger that is. We have to do some subtraction. Is what we're plugging into this thing. Okay. We're doing 13,750. We're going to add this crazy number, which is what, 1335. We do 30% of 4450, it should give us 1335. We add these two numbers together. We're going to get 1550. Okay. And so what we're talking about, if we make a salary of 68,000, we're going to get taxed 15,043.50. That doesn't seem right at all, but okay, so that is the final problem. This isn't my favorite problem, I will go to say. It's a little bit cumbersome, and I don't think it's a good example to introduce piecewise functions on. But there it is in all its glory. There's a little bit of weird stuff we have to do before we plug in a number, right? We have to know how much it's larger than this amount. This table's a little bit complicated to start introducing piecewise functions on, but I think it does give you a sort of maybe concrete, like a real world example of where piecewise functions are used, right? And so we do use piecewise functions, things change rates and stuff, and they come in handy for talking about these sorts of things. All right, see y'all soon. Study hard.